Thank you so much for coming to our EC tutorial, where we're going to be looking at what we're area of mechanism design, which we're calling partial mechanism design. And what we're thinking about here is an approach for mechanism design problems with equilibrium effects. So I'm going to be presenting the first half, where I'm basically going to be giving sort of an overview of the goal of this sort of strand of research, present a general framework and sort of general analysis. And then Xing is going to go through in the second half of the tutorial, sort of working through two concrete examples and then talking about some future directions. So I guess the sort of meta or background question that we have in mind in this research agenda is really, how can mechanism design inform real-world economic policy? And specifically what we're going to be thinking about is that in many cases, it's not the case that the entire economy or the entire set of markets that a policy has impact on is under the direct control over a policymaker or over a designer. And in reality, we often care about not just the direct impact that a policy is going to have in the market that's being designed, but also its equilibrium effects, and in particular, the indirect effects that it's going to have in other markets in the economy potentially. So to be more concrete, we can think about the following two examples. So the first example is, how should a firm optimally sell its goods? And what we're imagining is that there's potentially a downstream or a resale market. So in this case, we could think of a seller as our mechanism designer, and they have direct control over the primary market, but they don't necessarily have control over the downstream market or the design of resale markets. The equilibrium that the planner induces in the primary market is obviously going to affect the set of transactions that take place in the downstream market, and the participants in the primary market may potentially have expectations over what is going to then subsequently happen in that downstream market. So there's sort of this endogeneity where what happens in the downstream market is going to affect how participants then behave in the upstream market, and then the designer's choice of mechanism in the upstream market is then going to influence the equilibrium price that you eventually get in the downstream market. And then another case would be that maybe a social planner is thinking about how to optimally redistribute. Maybe they're designing the allocation for a public good, but there may also be a private market for that good that also operates. So the way that the planner then provides the public good is going to impact the equilibrium in the private market and vice versa. So in each of these examples, the mechanism designer can only design part of the market, and they need to account for these sort of equilibrium effects when they're thinking about the design of the optimal mechanism. So the sort of general framework that we're going to have in this sort of strand of research that we're presenting today is that we're going to assume that consumers can freely participate in the designed market and the allocations of the designed market are realized. So one example to have in mind might be a monopolist selling a final good to consumers, or maybe a monopolist is selling an input good to producers in an upstream market. Or we could think of a social planner selling public housing units to consumers. So that's sort of the first stage. And then the second part is that given the allocations that are realized in this design market, these agents then can freely participate in an undesigned aftermarket. So in particular, if we have, going back to our example that we've referenced on the previous slide, if a monopolist sells a final good to consumers, maybe consumers have the option to sell this final good in a resale market that operates following the primary market that was designed by the monopolist seller. Or if a monopolist has sold an input good to producers, then using this input, producers have the ability to then sell a final good to downstream consumers. And the price that is then realized for these downstream consumers and the outcome in this private market is obviously going to depend on the mechanism that was designed for allocating this intermediate good in the upstream market. And then in the case where we have a social planner selling public housing units to consumers, maybe consumers that are not allocated public housing can then participate in a private aftermarket for apartments. So the question that we want to ask is, how should the designer allocate the good in stage 1, given that there are these equilibrium effects? The allocation that's realized in stage 1 is going to affect the outcomes in stage 2 and vice versa. So the goal of this tutorial very broadly is to introduce a relatively new and rapidly growing research program. So there's been revived interest in applying large market mechanism design to applied problems, and we have sort of a variety of papers listed here. Ziyang is going to be presenting his job market paper in application number 2, and then Ziyang's also going to be presenting my job market paper that was joint work with Ziyang as application number 1 as we go through the tutorial. So there's a small subset of this larger literature which is looking at large market mechanism design in applied contexts that is specifically studying the equilibrium effects in these problems. And I also have a paper with Simon Locher where we're looking at what the optimal design for a primary market is when there is a resale market that operates following the primary market. So each of these 3 papers follow this general framework that I'm going to present shortly in the second part of my section. So what we're going to then focus on doing is develop this unified framework and show how we can essentially adapt classic tools for mechanism design in order to study these problems. And then Ziyang's going to conclude with some open questions. Okay, so let's go through the framework. And for the large part of the framework, it's going to look fairly standard. And basically what we're going to do is sort of massage things eventually in our analysis so that we're able to apply classic tools to then, for a mechanism designed to then characterize what the solution is for this general class of problems. So for the first part of the model, we're going to look at the consumer side. So there's going to be a unit mass of risk-neutral consumers that have unit demand and quasi-linear utility. And these consumers will differ in their type, which we'll denote by theta. And we're going to note the CDF of these types in the usual way by this capital F distribution. And we're going to assume that this distribution admits a positive density F everywhere on the support. And we're going to use this, again, pretty standard notation, this theta lower bar, theta upper bar notation to denote the support of the distribution. And as I was alluding to earlier, we're going to be thinking about at time t equals 1, our mechanism designer is going to be designing the primary market. And then following this primary market, there's going to be a realization of this aftermarket. And we're going to let P denote the price in this aftermarket. So we could think of so just to sort of fix ideas, we could think of the primary market as a monopoly seller, and we could think of the aftermarket as a resale market. And maybe we could have something like a perfectly competitive resale market, in which case this price P would simply be the equilibrium price in the perfectly competitive resale market that then operates after the realization of the primary market allocation. And so once we get to the second stage in this problem, then each of the agents is going to have a continuation payoff. So this is the payoff that is realized for these agents once the aftermarket has operated, and these continuation payoffs are naturally going to be a function of this equilibrium price P in the aftermarket. So we're going to use this V0 notation to denote the continuation payoffs as a function of both the aftermarket price P and the type for a given agent if they are not allocated the good in the design market. And V1, this again is a function of the aftermarket price P and the type theta of the agent if the agent is allocated the good in the designed market. So if we had T equals 1 being a primary market and T equals 2 being a resale market, then those who are allocated the good in the designed market would potentially become sellers in the resale market. So this would be the continuation payoff of agents who have the potential to enter this aftermarket as sellers. And if the agents are not allocated the good, then they're going to enter the aftermarket potentially as a buyer. And so this would be the continuation payoff of agents who enter the aftermarket as buyers. Just to sort of fix ideas, because at this point that the framework is a bit abstract, but as I said, Ziyang's going to go very concretely through 2 examples later on. Okay, so now from the mechanism designer's perspective. So we're thinking of a mechanism designer. They're going to choose a direct mechanism. Again, we're going to use standard mechanism design notation here. So we're going to let X and T denote our direct mechanism. And this consists of an allocation function, which is going to map our types to an allocation in the design market, where X theta is denoting the probability that a consumer of type theta receives the good. And then we have a payment function T. Again, this is mapping types to payments, and this is the expected payment that a consumer that reports to be of type theta makes in the design market to the mechanism designer. And then given the realization of the price P in the aftermarket, we're going to assume that the payoff of the mechanism designer is given by this expression. So it basically consists of 2 components, this capital pi 1 component and this capital pi naught component. So the capital pi 1 component, we can basically think of this as the component that's depending directly on the allocation that's realized in the design market. And so this, we're going to assume that this is some increasing function. And this is a function of essentially a standard virtual surplus function that's integrated with respect to, it's multiplied by the allocation that's induced in the direct market, and then is integrated with respect to the probability distribution of the types of the agents. And then the second component is the payoff. Then this is the payoff that depends on the realization in the aftermarket. So this is naturally, this is directly a function of the equilibrium price that arises in the aftermarket. And this first term is sort of indirectly a function of the aftermarket price in that this is obviously going to influence the types of the agents that participate in the initial market, because they're going to anticipate in equilibrium what's going to happen in the aftermarket as a function of the mechanism that's being chosen by the designer. And so as a result of that, the virtual surplus that applies in when the designer's designing the primary market, this is going to depend sort of indirectly on this aftermarket price P through the types of the agents, and so through this virtual surplus component. And so our key assumption is that this payoff function for the designer, or this function which will end up becoming the objective function of the designer, is an affine functional of our allocation rule X up to some increasing transformation. Okay, and so now I'm going to talk a bit about the aftermarket. Okay, so the price P in the aftermarket is going to depend on their mechanism through some function that's just a function of the allocation in the primary market. So remember our allocation rule, this is denoted by X. And we're going to denote the laissez-faire price by P0. So what we have is that if we don't allocate anything in the primary market, so if we have an allocation rule that's exactly equal to 0 in the primary market, then P0 is the price that we would then get in equilibrium in this aftermarket. And the idea, and this is going to be micro-founded further in the applications that Ziyang is going to present, is that the allocation X basically changes residual demand and supply in the aftermarket, and in equilibrium, the price in the aftermarket is going to be where residual demand, residual marginal revenue, is equal to residual supply. So very concretely, in the case where you have, say, monopoly pricing or a monopoly seller in the primary market, and then you have an aftermarket operating, then you can see very directly how the allocation is going to influence the residual demand and residual supply in the aftermarket. Those who the monopoly chooses to allocate the good to in the primary market are going to potentially act as sellers in the resale market, and those who are not allocated the good in the primary market would have the ability to act as buyers in the resale market. And so then very directly, the allocation rule that's induced in the primary market is again going to pin down what demand and supply are in the resale market, and thereby what the equilibrium price realization ends up being in the resale market. And our key assumption is going to be that the price in the resale market as a function of the allocation rule, this is going to be an affine functional of our allocation rule X again. So we're going to have essentially an affine objective, and then also we're going to have this affine functional, which is pinning down what the aftermarket price P is as well. Okay, and then in terms of the sort of key trade-off or problem that's then faced by the designer is that they basically face this trade-off between the direct effect versus the indirect effect of the policy. So what we're thinking about in terms of the direct effect, so this is the direct effect that the allocation has on the payoff or the objective of the designer holding the price in the aftermarket fixed. So in the laissez-faire case, in the case where the designer chooses to do nothing in the primary market, our representation for that allocation was just the zero allocation. So if we have the zero allocation and then holding fixed the price P in the aftermarket, and then here we have the actual allocation that's being induced, and P is then the equilibrium price in the aftermarket. So this is looking at the change in the payoff that happens as you go from the chosen allocation, as you go to the chosen allocation, away from the laissez-faire allocation, holding fixed the price P. The indirect effect is just looking at how the designer's payoff changes under the laissez-faire outcome, which is just an allocation of zero in the primary market, but now accounting for the price effect that happens as a result of the primary market or designed market allocation. And in particular, the indirect effect is the price in the aftermarket changing from this initial price P naught, that's the laissez-faire price, to the equilibrium price P that's induced under our given allocation rule X. And so naturally there's going to be, or the sort of non-trivial or interesting problems are going to be the case where we get this trade-off between this indirect effect and direct effect. And what we're going to be thinking about eventually is mapping out a frontier of feasible direct and indirect effects. And then naturally you want to sort of work out where this sort of Pareto frontier will end up being, so that for a given indirect effect, we're maximizing the direct effect and thereby maximizing the objective function of the designer. So essentially what we want to do is work out what combined direct and indirect effects are feasible, and then provide a characterization of this Pareto frontier, and then eventually work out, well, what the optimal mechanism then actually looks like. Okay. So moving on to the analysis. And as I said, what the analysis is going to involve doing is kind of successively sort of massaging the problem until we get to a problem that we end up being able to solve using relatively standard tools. Okay, so now a big picture question is, how should the designer allocate the good? And this is in the design market or the primary or initial market. And so to answer this question, we're going to proceed in two steps. The first thing is that we're going to choose some price P in the aftermarket that we want to induce in equilibrium. And equivalently, this is going to amount to choosing the indirect effect that we want to induce in equilibrium, because we're imagining that under laissez-faire, where there's zero allocation, P naught was our initial price, and then we're imagining, okay, what happens if we now choose the primary market allocation so that in equilibrium, we get this price P that's induced in the aftermarket. And the second stage is that we want to choose the mechanism we want to choose the best mechanism or the optimal mechanism from the perspective of the designer, subject to the constraint that the equilibrium price P in the aftermarket is consistent with our desire to choose this specific price P to induce in the aftermarket. So this is basically amounting to the chosen value of the indirect effect maximizing the value of the direct effect. So holding the price in the aftermarket fixed at P, we're going to maximize the first component, or the direct effect, which is what happens to the designer's objective as we move from the laissez-faire allocation, which is allocating nothing in the design market, to then moving to our chosen allocation X in the design market. And so as I was alluding to on our previous slide, basically what this is going to amount to is it's going to amount to tracing out this Pareto frontier. So for a given value of the indirect effect, which amounts to just choosing some particular price P that we're going to be inducing in the aftermarket, we then want to maximize the direct effect. So choose the allocation in the primary market subject to a sort of consistency, or something that's a bit analogous to, say, a Bayes plausibility constraint, where it needs to be the case that the chosen primary market allocation that maximizes this direct effect or this specific component that we've identified of the designer's objective function, subject to the constraint that it actually induces the presumed indirect effect or the presumed price P in the aftermarket. And so we want to do this essentially for all possible or feasible prices P in the aftermarket. So for the entire region of feasible indirect effects. And in this way, we're going to then trace out this Pareto frontier, which is telling us what the set of possible optimal mechanisms for the designer is then going to be. And then once we've traced out this frontier, then it's just a matter of working out, okay, now which corresponding size of the indirect effect or which corresponding price P in the aftermarket actually maximizes the overall objective of the designer. So essentially what we're going to be doing is mapping the problem that we initially started with, which you could maybe naturally think of as a fixed point problem, because potentially and in full generality, we would be looking at a mechanism design problem where both the types and the outside option of the agents that are participating in the mechanism potentially are endogenous to the mechanism itself through this dependence on what's happening in this aftermarket. We're going to take that problem, which is perhaps most naturally or initially thought of as a fixed point problem, and then map it to this nested optimization problem where the inner problem that we're going to be solving is essentially a constrained mechanism design problem. So what we want to do in terms of solving this sort of inner problem, or this constrained mechanism design problem, is that fixing a price P in the aftermarket, we want to maximize the objective of the designer, which in that case just collapses to maximizing this direct effect, subject to the constraint that we have our assumed value of the indirect effect, or completely equivalently, that we actually induce an equilibrium, the assumed price P in the downstream market. And then we also need to satisfy our standard incentive compatibility and individual rationality constraints as well. And so the next step in this problem is then going to be working out, okay, what do these IC and IR constraints actually look like in this inner problem? So incentive compatibility, very naturally, this is the constraint that ensures that each consumer reports their type truthfully. And then from a consumer's perspective, their payoff depends on their type. It depends on the allocation in the design market or in the primary market, and then it also depends on the price P in the aftermarket. And then by assumption, the dependence on the price P in the aftermarket appears through the dependence the dependence of the continuation values V1 and V0 on this price P in the aftermarket. So remember, V1 was our notation for the continuation value in the case where an agent is allocated the good in the design market or the primary market. So that would be this would be the payoff that pertains if X for that agent, or the allocation for that agent, is just equal to 1. But in general, X could be some probability between 0 and 1. So this ends up being this X ends up being the weight that we put on the continuation payoff V1 in this payoff function for the agents. And then V0, this is a continuation payoff if the agent isn't allocated the good in the primary market or the designed market. And that probability is just given by 1 minus the allocation rule. And then here we're just subtracting off the payment that the agent's making for the designer. So if the agent chooses to report to be of a type theta prime, but their true type is actually theta, then these continuation payoffs depend on the true type, but then the actual realized allocation and the payment that's made to the planner, these depend on the type that the agent actually or that the consumer actually reported. And then what we want is this expression to be maximized under truthful reporting. So when the agent actually reports their true type, theta prime equal to theta. So that's the incentive compatibility constraint. And I guess the main part, which is sort of non-standard, is this component which is depending on 1 minus the allocation rule. And then the individual rationality constraints, these can be constructed in a similar way. So consumers participate in the designed market voluntarily. So it has to be the case that the payoff that they get from participating in the designed market under truthful reporting, which I've printed out here, is equal to or greater than the payoff that they get from just directly participating in the aftermarket. And that continuation payoff is given by evaluating V0 at the equilibrium price that's induced in the downstream market P, and then that's also a function of the agent's type by assumption. So that's that individual rationality constraint. And as I was also highlighting with the incentive compatibility constraint, the sort of non-standard component here is first this dependence on the continuation payoff that arises if the agent isn't allocated the good in the designed market or the primary market. Usually we would assume that this is just 0 because everything's under the control of the designer. But in this partial mechanism design problem, this component of the utility functions or the payoff functions of the agents is not directly under the control of the designer. And then also potentially agents can just directly participate in the aftermarket bypassing the mechanism that's been offered by the designer, and the designer has no way of preventing that, but what they can do is influence the sort of trading position or the allocation of that agent when they enter the aftermarket. So that's why we get this dependence on the payoff if the agent doesn't participate in the mechanism, just directly on the equilibrium payoff that agent would then get in the aftermarket. So what we basically have here is again a problem where we have this type-dependent outside option, and that outside option is actually also endogenous to the mechanism that's been chosen in the designed or the primary market. Okay, so then what we can do next is move towards applying a version of the payoff equivalence theorem or the envelope theorem. And so the first thing that we're going to do is basically rearrange our incentive compatibility constraint so that we collect the components that directly depend on the allocation, because eventually we want to get to a stage where we're going to rewrite everything just in terms of some objective or some modified virtual surplus function for the designer, and then we want it to depend linearly on the allocation rule overall. So what we're going to do is we're going to gather these terms in the incentive compatibility constraint that depend on the allocation. So that's what we've done here. And then what this does is it introduces, or we can identify what we're going to then call an effective type for the agent. And so this effective type, this is equal to the difference between their continuation values when they're allocated versus not allocated the good in the primary market. And this is the component of their payoff function that depends on the allocation rule. And this effective type is basically the type that the agent is going to actually have the ability to screen over, because the only thing that the designer is able to influence is this primary market allocation or this direct allocation X. But that's going to have this influence on both the continuation payoffs if the agent is versus isn't allocated the good in the primary market. And so this effective type is then essentially or intuitively the type that the designer actually has the ability to screen over when they're thinking about the optimal selection of the mechanism in the primary market or the design market. And then we can do a similar thing with the individual rationality constraint. We can basically gather the component that depend, or we can gather the components that depend directly on our allocation rule. And again, is given by this difference between the continuation payoff if the agent is versus isn't allocated the good in the direct or the primary market. So again, we get this incentive compatibility constraint that now depends on this effective type. And once we've done this sort of step of identifying what these effective types are, that the designer actually has the ability to screen over, accounting for the equilibrium effects of what happens in the aftermarket, then the problem is now moving closer and closer to looking more like just a standard mechanism design problem and standard incentive compatibility and individual rationality constraints. And so, as we've noted here, without loss of generality, the designer basically considers mechanisms that elicit only information about this effective type. Okay, so then we can basically go through a series of standard mechanism design arguments to show that Meyerson's lemma still applies if we basically make this change of variables from the actual types of the agents to these effective types of the agents, the effective types being the types that the designer has the ability to screen over. And then we get this sort of nice and again very standard looking characterization of incentive compatibility, where a given mechanism is going to satisfy incentive compatibility and individual rationality if and only if we have a non-decreasing allocation rule, where we've written the allocation rule now essentially as a function of the effective types rather than being a function directly of the true types. And then also this modified payment rule, where again we're modifying the payment rule so that now it is a function of the effective type, which is the type that the designer actually has the ability to screen over, rather than writing it directly as a function of the true type. And then this last equation here, this is basically now just applying the envelope theorem to this, or the envelope formula to this problem. So we basically get this sort of standard characterization of incentive compatibility in terms of having a non-decreasing allocation rule, just writing allocation rules as a function of effective types, and then this characterization of the local incentive compatibility constraints in terms of this envelope formula. Okay, and so now we're moving towards being able to characterize what the optimal mechanism actually looks like. And so our main theorem is that now there exists an optimal mechanism, which we're going to denote by X star T star, that is a menu of at most 2 prices. And in particular, what this implies is that the image of this optimal allocation rule is going to contain at most 3 elements, 0, pi, and 1. This is for some pi that lies strictly between 0 and 1. So in particular, what this implies is that the optimal allocation is going to potentially involve giving or allocating the good with certainty to some types, not allocating the good with certainty to some types, and then rationing some of the types. So allocating them the good with probability pi. And then the optimal, and this is just explaining in words or printing out what I just explained in words. So the optimal mechanism just then ends up having this very simple structure where consumers in equilibrium who pay a higher price are going to receive the good with probability 1, and then consumers who pay the lower price will receive the good with some intermediate probability pi, and then those who are not allocated the good and get this allocation of 0 are obviously not going to be paying any transfer to the designer. So this, and Deang will talk about this in more detail in the context of the applications, but this theorem, essentially, we can think of it as providing basically a new justification for rationing. So in this problem, the designer faced this trade-off between the direct and indirect effects, and then as a result of the constraint that this then introduces into this inner problem that the designer is solving, this is then why we might end up with a designer that then elects to ration in equilibrium. Okay, And so basically, in order to prove this result, what we need to do is we need to rewrite the objective function of the designer in terms of these effective types. So that's what we do. That's what we're doing here. So we rewrite everything. So we have our virtual, what was previously our virtual surplus function. But what we need to do now is, in order to sort of transform the objective function in the appropriate way, is work out the expected value of this virtual surplus function conditional on realization of the effective type. And then we've got our effective allocation rule. So that was our modified allocation rule that's actually written in terms of these effective types. And then G here is just denoting the distribution of these effective types. And then we have two constraints in this problem. We have the first constraint. This is the standard monotonicity constraint that arises as a result of our characterization of incentive compatibility. The sort of envelope theorem part and the local incentive compatibility constraints are going to be already embedded into the calculation of the virtual surplus function. And then the second and more novel constraint is the constraint, or this sort of consistency constraint or base plausibility constraint. And this is requiring that the allocation rule that the designer is choosing actually induces the assumed price P in the downstream market, because only if P is the price that's induced in the downstream market is this expression for virtual surplus actually valid or consistent. And so what we end up with here is basically an infinite dimensional linear programming problem where both our objective and our constraint are affine in this effective allocation rule. This allocation rule has been written as a function of these effective types. And the linearity of the objective and the constraint, they're basically going to follow from the assumptions that we made earlier, where we had our sort of unmassaged problem, or our problem that was written as essentially a fixed point problem where everything was just written initially directly in terms of the types rather than the effective types. We assumed that that version of the problem was such that our objective and our constraint were linear, and then that property then ends up carrying over to this version of the problem where we've written everything in terms of effective types. And so any extreme point of this feasible region then ends up satisfying this property that the image of the extreme point it has these three elements, 0, pi, and 1, where pi is somewhere between 0 and 1. So basically, instead of a world where we get the optimality of a sort of posted price mechanism, or the image of the optimal mechanisms just being 0 and 1, the fact that we have this constraint here, this is basically then what ends up introducing the possibility that we may actually have rationing under the optimal mechanism. This is what expands the sort of dimension of the extremal points of the feasible region once we account for the fact that we have this constraint. So you can think of this as sort of a Carathéodory's theorem style argument. All right, and then that's all that I have for the first part. So I'm going to hang around a little bit, and Ziyang will be here hopefully as long as his internet connection is also remaining stable, and then we'll come back for the second part of the tutorial where Ziyang is going to go through sort of two papers in detail. My job market paper that's co-authored with Ziyang, and then Ziyang's job market paper, and sort of applying the framework and the results that we just went through that was fairly abstract to more concrete examples. So thank you.